So we have seen the mathematics for the MAP and the ML selection or optimization criteria. We've seen it in the case of the linear sampling receiver, and more recently we've seen it in the case of the signal space analysis. And I mentioned in there that for the binary case, the two give the same results. And now I'd like to show you that the two give the same results, and we have sort of a name for this equivalency. And in the case of the linear sampling receiver, so here we had the linear sampling receiver. We said we would use a match filter. And what I'm going to show you now is we have another name, Correlator, for the structure that we found using signal space analysis. So at first glance, these two seem perhaps like different solutions. One is to use a vector representation, and we're going to call that a correlator. We'll show you what that definition is. And in the other case was use a match filter. And then what we're going to show you now is that mathematically these two give exactly the same results, which it should, because they're both applying the same optimality criteria, but just using a different set of mathematics to arrive at that conclusion. So the equivalence of the match filter and the correlator is also covered in section 3.2. It's covered in Appendix B, gives some of the math for the MAP and maximum likelihood, and in the course notes, of course, we discuss this equivalence. So the two approaches, again, the first one was a linear sampling receiver. We fixed the type of receiver. Once we fixed this type of receiver, gave the block diagram, you pass it through a filter, you do a sampling, and then you compare with a threshold. We use probability theory to decide what that threshold is, what the decision rule is. Afterwards, we went through a development to try and find out, well, that filter we're using, what would be the best filter, and we came up with what we called a match filter, that whatever symbol waveform we used, we should use the same one at the receiving filter. That was approach one. Approach two was to instead introduce the idea of signal space analysis. In signal space analysis, we took used a vector space to represent the symbol transmitted, the noise, the signal received. We used the same probability theory to come up with a decision rule. But in this case, we came up with a structure which is a correlator. And what do I mean by a correlator? I'll be explaining that. So sampling receiver, this is the block diagram. Filter, sample, compare with the threshold. The filter that we came up with was one that was matched to the symbol transmitted, and so here it is, a impulse response which is determined by the shape of the symbol waveform. Now, if we take our math and come up with what the decision statistic is that is being used here, we would take the received signal, we would convolve it with the filter, which of course is matched to the symbol transmitted, and we would get an integral of the received signal correlated, here we get the word correlation, where we multiply it with a symbol waveform. Now, because of the correlation, instead of just being capital T minus T, because of the correlation, we should replace T with T minus Z as part of this integral over dz. So when I plug this in and I evaluate this, I do the sampling at time capital T. Well, if I do the capital T timing for T, then here I get capital T minus capital T. And minus z, so I come up with this very simple expression. So the choice of making a matched filter here means that when I do this sampling at the symbol time, that this test statistic that I'm getting, this test statistic that I'm going to use to compare with a threshold, just simplifies to this integral, the integral from 0 to t of r of z times SI of Z dz. So that would be, conditioned on I being sent if I was really sent, this is what this test statistic would look like. So this is just taking the results of a matched filter and looking at what does the test statistic look like. So that's what it looks like. And now we're going to see that this looks very much like what we're also working with in the signal space analysis. I said that I would define what is a correlator, and I guess now's the time to do it since we really see now the form of what we call a correlator. So a correlator would be something where we take something in, we multiply it, and then we do an integral of it. This is the block diagram of a correlator. So in this expression, what we're seeing is that what comes in is the received signal, and that I take this received signal and I correlate it with SI of t. And then I integrate it. So here's the correlation. I multiply them together and then I integrate over the integral. And this becomes my test statistic. So the sampling receiver is what we call a matched filter because it's filters and then it samples. But it's really the equivalent if I had said to you, forget this structure, take the received signal, correlate it with the with one of the transmitted symbols and get an output. So why is this important? Because this is the inner product in signal space. This is the definition of the inner product. 0 to t, r of t, si of t, dt. So an inner product is essentially a correlator. So an inner product is a correlator, and the match filter looks like it's very similar to the correlator. Okay, so correlator, match filter are equivalent. And it's really equivalent just because we sample it this time. So another way of trying to look at this is, what is the convolution? The convolution is, I'm convolving R of t with S of t, so I take S of t, I flip it and I slide it. And then if I take the output of the match filter, this is just an illustration, not a specific example, but I might have something that's growing like this. Now, if I took the correlator output, it would be more monotonic, getting larger. But the important thing is that when I sample at time t, these two coincide. That this calculation, match filter, which the filter before I sample it, it's a time-varying signal that's coming out of my filter. But then I sample it at a certain time. Sampling it at a certain time gives me the same output if I run a correlator and the integration is over that same time interval. So match filter, correlator, essentially the same idea. When I implement them, it's different, right? Once I use a multiplier and then I use an integrator, and the other one I do a filter and then a sample. So the implementation, the hardware could be different in these two solutions, but mathematically they give the same result. And if you're looking at different texts, they may say it's a match filter and then they may show you the implementation of a correlator. It's okay, because the two are equivalent, but sometimes people mix the language and they'll call it a match filter although their implementation is not a filter. Which all brings us back to our signal space. Why did we go through this effort to represent it in signal space? And I, again, recall that the reason we go through the signal space approach as opposed to the other is because of the intuition it gives us of using a geometric space to represent the position of different symbols. And it's because this correlation is more intuitive because of the relationship between correlation and distance. So I'm going to recall for you now why this correlator structure, how it applies to the signal space. I mean, I already showed you that it was the inner product, right? So now let's look at the math for the two kinds of optimizations, the maximum likelihood a posteriori and the maximum likelihood. In this case, we had the L2 norm that we were looking at. So how can I see now that when I'm looking at these structures, okay, this is the math. It says minimize this representation in signal space. But that is a structure, and the structure is going to be the correlator structure. It's going to be the inner product structure. How do I actually implement this? I could implement actually calculating distances, but it's easier to use the inner product. So if I were to take the L2 norm and write it, I could write it in this way. It's the L2 norm of R and the L2 norm of S, and then I have to subtract the inner product of the two. In this case, for the map, I also have this weighting term, which is changing these, but in the case of the maximum likelihood, it would really just be these three terms. So the distance between the received vector and each one of the possible transmitted vectors would be this. I'd have to calculate it, m times. But when I look at that, this is going to be the same in every calculation. So this part in green doesn't change when I'm trying to minimize, right? I'm trying to minimize, I'm trying to find out which SI minimizes this distance, which one was closest. Well, when I do that, the length of R doesn't change in any one of this. I compare it, I compare it, I compare it. So that doesn't change. This is the energy, essentially the energy of each one of the symbols. Well, why should I calculate that every single symbol transmitted? Because I know this ahead of time. I know that I have M symbols, and these M symbols have a certain energy. This is just my strategy. I'm going to use this strategy. So these are known ahead of time. Remember, every time I get an R, every time I receive every single symbol transmitted, I have to calculate this distance, and that's computationally expensive. But now I'm thinking, well, I don't have to do this whole calculation, because if I look at these three terms, these two terms, well, this one doesn't matter because it doesn't change, so why should I calculate it? And this one, why should I calculate it each time? I know it. So those are just stored. So really, the only thing I have to calculate every time is this inner product. So that's why in the implementation phase of this vector space approach, essentially I'm saying what I should build is a correlator. I should build a correlator that will give me, the values that I need in order to make a decision on either the map or the maximum likelihood. So finally, using the vector space analysis and this argument, we can see that it is a correlator. I showed you correlator by name is an inner product, and the correlator, this inner product, is what's really coming up as having to be calculated for this strategy in vector space. So now we see how these two approaches come together. The match filter is essentially a correlator, and the vector space approach essentially needs the calculation of the correlation. So this is our correlator structure. So we've seen that the signal space analysis essentially tells us we should be using a correlator structure. And so if we're going to implement this signal space analysis, what we would do is we would take the received signal, and I'm not sure which one was transmitted, so I take the received signal, I split it into, if there are M symbols transmitted, I split it into M different branches. Each one of the branches, I calculate a correlation with each one of the symbols. And then in the case of maximum likelihood, I would just choose the largest. If it was a map, I would say choose the largest modulo some weighting due to the a priori probabilities. So that is why we come down to the equivalence of these two approaches, because essentially sampling of this match filter is going to give me the same number as if I had done the calculation with the correlator. They're going to give me the same number. So it's the same receiver. So even though previously I gave you the structure of a match filter, if we had just done the signal space analysis, we would just say it's a correlator. But now we know that there's these two approaches that give the same result, and we have two different implementations we might be able to use.